that. Stars will restore order as these writers. Coming out, they're coming out. Flag was proudly protest. The American flag was really nowhere to be seen unless it was being set alight. They proudly fly the Mexican flag, but they burn the American one. Exported to Mexico and other countries they hold in. What they do, whether it's Antifa,
WSP,
BLM, or they flawless, remember the violence as soon as Trump became president. The first.
Alright, guys, we're doing a studying stream. Start my YouTube. I'm gonna do it. UK. American. That's funny.
BTW wanna know what happened to hacks? What's algebra?
Basically a system of equations that could actually just search it up. Expression, but give me a
AM just in primary, bro. Primary 4.
dang. What primary 4 is look for?
It's all about solving problems. It's not about, like maybe in previous years you've done multiplication table memorization. It's not like memorizing how to solve problems. It's learning the tools of how to solve problems and then using them and building them up in creative ways. So it's kind of like, it really does remind me of art, because if you are doing like a painting or something, you have like a specific tools about like maybe paintbrushes or different techniques you can use to create something bigger. So I feel like algebra is really all about combining things that you already know how to do into something bigger.
So the word algebra comes from the Arabic word al-jabr, that literally translates to reunion of broken parts. This breaking apart of mathematical representations and putting it back together in the form of balanced equations is the essence of algebra. And the beautiful thing is that this balancing
Algebra
and solving
important.
of equations can be done in
Yeah, algebra. See, I said what they said. It's what leads you. Bro. Yeah, ignore all those searches. That's just funny. It sharpens critical thinking, problem solving skills. Engineering, technology. Do tech stuff, but I really want to do tech stuff. The skill to be able to
Just math, but
have
harder.
this right here.
Many different ways, which is
Trigonometry.
where creativity comes in.
This right here is a picture of René Descartes. Once again, one of the great minds in both math and philosophy. And I think you're seeing a little bit of a trend here that the great philosophers were also great mathematicians and vice versa. And he was somewhat of a contemporary of Galileo. He was 32 years younger, although he died shortly after Galileo died. This guy died at a much younger age. Galileo was well into his 70s. Descartes died at only 54 years old. And he's probably most known in popular culture for this quote right over here, a very philosophical quote. I think, therefore I am. But I also wanted to throw in, and this isn't that related to algebra, but I just thought it was a really neat quote, probably his least famous quote, this one right over here. And I like it just because it's very practical. It makes you realize that these great minds, these pillars of philosophy and mathematics, at the end of the day, they really were just human beings. And he said, you just keep pushing. You just keep pushing. I made every mistake that could be made, but I just kept pushing, which I think is very good life advice. Now, he did many things in philosophy and mathematics, but the reason why I'm including here as we build our foundations of algebra
What is he saying?
is the individual most responsible for a very...
You can't hear him? All that.
very strong connection between algebra and geometry.
You could hear him.
So on the left over here, you have the world of algebra.
You could hear him.
We've discussed it a little bit. You have equations that deal with symbols, and these symbols are essentially, they can take on values. So you could have something like y is equal to 2x, y is equal to 2x minus 1. This gives us a relationship between whatever x is and whatever y is. And we can even set up a table here.
That was high pitch and K think he's saying that too fast location yellow teal bars.
And I could just pick random values for x and then figure out what y is. But I'll pick relatively straightforward values just so that the math doesn't get too complicated. So for example, if x is negative 2, then y is going to be 2 times negative 2 minus 1. 2 times negative 2 minus 1, which is negative 4 minus 1, which is negative 5. If x is negative 1, then y is going to be 2 times negative 1. 2 times negative 1 minus 1, which is equal to, this is negative 2 minus 1, which is negative 3. If x is equal to 0, then y is going to be 2 times 0 minus 1. 2 times 0 minus 1 is just negative 1. I'll do a couple more. If x is 1, and I could have picked any values here. I could have said, well, what happens if x is the negative square root of 2? Or what happens if x is negative 5 halves? Or positive 6 sevenths? But I'm just picking these numbers because it makes the math a lot easier when I try to figure out what y is going to be. But when x is 1, y is going to be 2 times 1 minus 1. 2 times 1 is 2, minus 1 is 1. And I'll do one more. I'll do one more in a color that I have not used yet. Let's see, this is purple. If x is 2, then y is going to be 2 times 2. Now our x is 2 minus 1. Minus 1. So that is 4 minus 1 is equal to 3. So fair enough. I just kind of sampled this relationship. I said, okay, this describes a general relationship between a variable y and a variable x. And then I just made it a little bit more concrete. I said, okay, well then if x is one of these variables, for each of these values of x, what would be the corresponding value of y? And what Descartes realized is that you could visualize this. One, you could visualize these individual points, but that could also help you in general to visualize this relationship. And so what he essentially did is he bridged the worlds of this kind of very abstract symbolic algebra and geometry, which was concerned with shapes and sizes and angles. So over here you have the world of geometry. And obviously there are people in history, maybe many people who history may have forgotten, who might have dabbled in this. But before Descartes, it's generally viewed that geometry was Euclidean geometry. And that's essentially the geometry that you study in a geometry class in 8th or 9th grade or 10th grade in a traditional high school curriculum. And that's the geometry of studying the relationships between triangles and their angles and the relationships between circles, and you have radii, and then you have triangles inscribed in circles and all the rest, and we go into some depth in that in the geometry playlist. But Descartes says, well, I think I can represent this visually the same way that Euclid was studying these triangles and these circles. He said, well, why don't I, if we view a piece of paper, if we think about a two-dimensional plane, you could view a piece of paper as kind of a section of a two-dimensional plane. We call it two dimensions because there's two directions that you could go in. There's the up-down direction, that's one direction. So let me draw that. I'll do it in blue because we're trying to visualize things. So I'll do it in the geometry color. So you have the up-down direction, and you have the left-right direction. That's why it's called a two-dimensional plane. If we were dealing in 3 dimensions, you would have an in-out dimension. In-out. And it's very easy to do 2 dimensions on the screen because the screen is 2-dimensional. And he says, well, there are 2 variables here, and they have this relationship. So why don't I associate each of these variables with one of these dimensions over here? And by convention, let's make the y variable, which is really the dependent variable. The way we did it, it depends on what x is. Let's put that on the vertical axis. And let's put our independent variable, the one where I just randomly picked values for it to see what y would become, let's put that on the horizontal axis. And it actually was Descartes who came up with a convention of using x's and y's, and we'll see later z's in algebra so extensively as unknown variables, or the variables that you're manipulating. But he says, well, if we think about it this way, if we number these dimensions, so let's say that in the x direction, let's make this right over here. This right over here is -3. Let's make this -2. This is -1. This is 0. Now I'm just numbering the x direction, the left-right direction. Now this is +1. This is +2. This is +3. And we could do the same in the y direction. So let's see, so this could be, let's say this is -5, -4, -3, actually let me do it a little bit neater than that. Let me clean this up a little bit. So let me erase this and extend this down a little bit so I can go all the way down to -5 without making it look too messy. So let's go all the way down here. And so we can number it. This is 1, this is 2, this is 3, and then this could be -1, -2. And these are all just conventions. It could have been labeled the other way. We could have decided to put the x there and the y there and make this the positive direction, make this the negative direction. But this is just a convention that people adopted, starting with Descartes. -2, -3, -4, and -5. And he says, well, I think I can associate I can associate each of these pairs of values with a point in 2 dimensions. I can take the x coordinate, I can take the x value right over here, and I say, okay, that's negative 2. That would be right over there along the left-right direction. I'm going to the left because it's negative, and that's associated with negative 5 in the vertical direction. So I say the y value is negative 5, and so if I go 2 to the left, and 5 down, I get to this point right over there. So he says these two values, negative 2, negative 5, I can associate it with this point in this plane right over here, in this two-dimensional plane. So I'll say that point has the coordinates, tells me where to find that point, negative 2, negative 5. And these coordinates are called Cartesian coordinates, named for Rene Descartes. He's the guy that came up with these. He's associating all of a sudden these relationships with points on a coordinate plane. And then he says, well, okay, let's do another one. There's this other relationship where I have when x is equal to negative 1, when x is equal to negative 1, y is equal to negative 3. So x is negative 1, y is negative 3. That's that point right over there. And the convention is, once again, when you list the coordinates, you list the x coordinate, then the y coordinate. And that's just what people decided to do. Negative 1, negative 3. That would be that point right over there. And then you have the point when x is 0, y is negative 1. When x is 0, right over here, which means I don't go to the left or the right, y is negative 1, which means I go 1 down. So that's that point right over there. 0, negative 1, right over there. And I could keep doing this. When x is 1, y is 1. When x is 1, y is 1. When x is 2, y is 3. When x is 2, y is 3. Actually, let me do that same purple color. When x is 2, y is 3. 2, comma 3. And then this
Fire.
one right over here in
I'm
orange
trying to
was 1,
learn
comma
to.
1. And this is neat by itself. I essentially just sampled possible x's. But what he realized is not only do you sample these possible x's, but if you just kept sampling x's, if you tried sampling all the x's in between, you would actually end up plotting out a line. So if you were to do every possible x, you would end up getting a line that looks something like that, right over there. And any relation, if you pick any x and find any y, it really represents a point on this line. Or another way to think about it, any point on this line represents a solution to this equation right over here. So if you have this point right over here, which looks like it's about x is 1.5, y is 2. So let me write that. 1.5, 1.5, comma 2. That is a solution to this equation. When x is 1.5, 2 times 1.5 is 3, minus 1 is 2. That is right over there. So all of a sudden, he was able to bridge this gap or this relationship between algebra and geometry. We can now visualize all of the x and y pairs that satisfy this equation right over here. And so he is responsible for making this bridge. And that's why the coordinates that we use to specify these points are called Cartesian coordinates. And as we'll see, the first type of equations we will study are equations of this form over here. And in a traditional algebra curriculum, they're called linear equations. Linear equations. And you might be saying, well, okay, this is an equation, and I see that this is equal to that, but what's so linear about them? What makes them look like a line? And to realize why they are linear, you have to make this jump that Rene Descartes made. Because if you were to plot this using Cartesian coordinates on a Euclidean plane, you will get a line. And in the future, we'll see that there's other types of equations where you won't get a line. Well, you'll get a curve or something kind of crazy or funky. I'm here with Jesse Rowe, who's a math teacher at Summit San Jose and a Khan Academy teaching fellow. And you had some interesting ideas or questions.
Yeah, one question that students ask a lot when they start algebra is, why do we need letters? Why can't we just use numbers for everything?
Why letters? So like, why do we have all these X's and Y's and Z's and ABCs when we start dealing with algebra?
Yeah, exactly.
That's interesting. Well, why don't we let people think about that for a second?
How would it represent something?
So Sal, how would you answer this question? Why do we need letters in algebra?
So why letters? So there's a couple of ways I'd think about it. One is if you have an unknown. So if I were to write x plus 3 is equal to 10. The reason why we're doing this is we don't know what x is. It's literally an unknown, and so we're going to try to solve for it in some way. But it did not have to be the letter x. We could have literally written blank plus 3 is equal to 10. Or we could have written question mark plus 3 is equal to 10. So it didn't have to be letters, but we needed some type of symbol. It literally could have been smiley face. Smiley face plus 3 is equal to 10. But until you know it, you needed some type of a symbol to represent whatever that number is. Now we can go and solve this equation and then know what that symbol represents. But if we knew it ahead of time, it wouldn't be an unknown. It wouldn't be it wouldn't be something that we didn't know. So that's one reason why I would use letters. And where just numbers by itself wouldn't be helpful. The other is when you're describing relationships between numbers. So I could do something like, I could say that whenever you give me, if you give me a 3, I'm going to give you a 4. And I could say if you give me a 5, I'm going to give you a 6. And I could keep going on and on forever. If you give me a 7.1, I'm going to give you an 8.1. And I could keep listing this on and on and on forever. Maybe you could give me any number and I could tell you what I'm going to give you, but it would obviously, I'd run out of space and time if I were to list all of them. And we could do that much more, I guess, elegantly if we used letters, if we describe the relationship. Maybe what you give me, we call X, and what I give you, we call Y. And so I say, look, whatever you give me, I'm going to add 1 to it, and that's what I'm going to give back to you. And so now this very simple equation here can describe an infinite number of relationships between X, or an infinite number of corresponding Y's and X's. So now someone knows, hey, whatever X you give me 3, I add 1 to it, and I'm going to give you 4. You give me 7.1, I'm going to add 1 to it and give you 8.1. And so there's no more elegant way that you could have done it than using symbols. With that said, I didn't have to use X's and Y's. This is just a convention that kind of comes to us from history. I could have defined what you give me as star, and what I give you as, I don't know, as smiley face. And this also would have been a valid way to express this. So the letters are really just symbols, nothing more.
Okay, guys. So that's why letters are in algebra. Sub lesson 2. Variable is, and then tomorrow we'll study a little more. See what you guys picked up from what a variable is, some others, and then this is when we start using this right here, evaluating expression. Yes.
Let's say that I'm working in a restaurant and I'm making $10 per hour, but on top of my hourly wage, I also get tips each hour. So this entire expression, you can view this as how much I might make in a given hour. Now, you might also realize that the number of tips, or the amount of tips I might make in an hour, can change dramatically from hour to hour. It can vary. 1 hour, it might be lunchtime, get a lot of tips. People might get some big ticket items. The next hour, I might not have any customers, and then my tips might be really low. So the tips part right over here, we consider that, the entire word, we consider that to be a variable. From scenario to scenario, it can change. So for example, in one scenario, maybe it's lunchtime, I'm getting really big tips. So tips is equal to, let's say it's equal to $30. And so the total amount I might make in that hour is going to go back to.
Alright, see ya, Jelly.
this expression right over here, it's going to be 10 plus, instead of writing tips here, I'll write 30 because that's what my tips are in that hour. And so that is going to be equal to, it's going to be equal to 40. Let me do that. Let me do it in that yellow color. It's going to be equal to $40. But let's say right after that, the restaurant slows down. We're out of the lunch hour for whatever reason. Maybe the restaurant next door has a big sale or something. And so the next hour, my tips go down dramatically. My tips go down to $5 for that hour. Now I go back to this expression. The total I make is my hourly wage plus the $5 in tips, plus the $5 in tips, which is equal to $15. As you see, this entire expression, the 10 plus tips, it changed depending on what the value of the variable tips is. Now, you won't see whole words typically used in algebra as variables. We get lazy, and so instead we tend to use just easier to write symbols. And so in this context, instead of writing tips, maybe we could have just written 10 plus t, where t represents the tips that we get in an hour. And so then we would say, okay, what happens when t is equal to 30? Well, if t is equal to 30, then we'd have, let me write, so what happens when t is equal to 30? Well, then we have a situation, t is equal to 30. This evaluates to 10 plus 30, which would be 40. What would happen if t is equal to 5? Well, then this would evaluate to 10 plus 5, which is equal to 15. Now, I want to be clear. We didn't even have to use t. We didn't even really have to use a letter, although in traditional algebra, you almost do use a letter. We could have written it as 10 plus x, where x is your tips per hour. X might not be as natural. It's not the first letter in the word tips. Or you could have even written 10 plus star, where you could say star represents the number of tips in an hour. But it just might have not made as much intuitive sense. But hopefully this gives you a general idea of just what a variable is. All it is a symbol. All it is a symbol that represents a symbol that represents varying values, and that's why we call it a variable.
All right, guys. So we're gonna learn today, and then tomorrow we're gonna be learning why we're using the multiplication sign, etc. In parentheses, yeah, parentheses, this, yeah. All right. Do a Kahoot real quick. Type in the chat if you want to do a Kahoot. If you do not want to do a Kahoot, then we don't have to do a Kahoot. We don't have to. Make sure to type in the chat if you want to do a Kahoot. We could all do a Kahoot. The fact that they left means that they don't need a Kahoot.